we haven't really discussed this.
Yes.
Am I right? Yes. So, okay. So let us just quickly start. We have quite a lot to do today. Quite a lot to do today, but we'll see how far we can go. So, course rep, if I may ask, is there so what have you people done so far? Have you guys done the tests of significance and all that? Who is the rep? Hello?
No.
Has Professor Maduka taken her classes?
Yes, she has.
She's not the one supposed to take all this chi-square correlation, all that t-test.
I think it's taught at interquartile range, from what I can remember.
Okay. She was actually supposed to take inferential statistics, but when she asked and we said we have not gone far, so she had to start all over from the basics.
Okay, so what did she say now? So let me just know if she has taken central tendency and dispersion, there's no need to repeat it now. So has she done that? Or did she do that?
Yes, she did.
Yes, she tried to go through measure of central tendency, measure of dispersion, normal curve, the Gaussian curve. These are the things. Yes.
Okay, that means she has helped me now. Okay, so what I will just do, since it's assumed
we
that
don't know. Sorry, sir, we don't know the depth to which it was supposed to be taken. We know she mentioned those things, but we can't be sure of the depth.
So, because we need to go into some basic, more in-depth stuff. So if she has taken that, then there will not be need to start repeating and repeating. Anyway, so I will just. So let me just do.
Mentioned it, sir.
Which one is mentioned? Which one is
only mentioned it?
No, she taught it though.
Which one is mentioned? Did she mention it or did she teach it? Well,
she taught it.
It wasn't really in depth. It wasn't really in depth, sir.
Which one is in depth? She has done it.
She taught it. We even did calculations.
She's teaching now.
She taught us central measures of central tendency.
She has done measures of central tendency.
Okay. So
move forward.
Oh, you already have the slides. I'm sure she sent you hers. I've sent you mine as well. So
yes.
So we will just start and go on with that. So I'll just do a brief overview to just refresh your memory. So that you have the slides. She has taught it. She gave you guys examples to solve. So how else? She has taught it then. Anyway, so measures of central tendency, you can have. So when you have data, you want to summarize it, right? So you want to ensure that the data makes sense, and that's where the data summary measures come in. So you have the measures of central tendency and the measures of variability or spread. So if you have 1,500 individuals, you measure their heights, for example, you have heights of 1,500 individuals. So you will now but if you want to now summarize the data, you summarize it in a single figure that will give you an idea of the center of the data. So that's the concept of the measures of central tendency. But most times we don't report only the measure of central tendency, we report the measure of spread as well, because yes, a value that gives you an idea of where the center of the data is, but you want to know the degree of spread of the values of the data set. So that's where the measure of variability comes in, right? So just as you know, you have the mean, you have the median, you have the mode, and that is these are the measures of central tendency. When we talk about the mean, we're just talking about the average, the arithmetic mean. The other types of mean, but that's not really what we'll be focusing on. So we'll be focusing on the arithmetic mean. We're focusing on the arithmetic mean. Then we have the median and we have the mode. So these slides have already gone ahead. So I want to believe that you've at least studied it based on not just mine, the one also Professor Maduka gave to you. I'm sure you've studied it as well. Well, I'm just giving like a general overview. For the arithmetic mean, so that we can go into some other more this thing. So for the arithmetic mean, you're just taking the average. That is for ungrouped. So for a data set, you can have grouped and ungrouped data. So for the ungrouped data, that is just single data like that from the individual participants. But when you have grouped data, for grouped data, you have grouped them into categories. So that's the group data. And then the approach to the summary, right, for ungrouped and grouped data is quite different. That's the formula for that. So I want to believe that you have studied these slides at least, so that we can just, any area that maybe one or two people you don't understand, we just discuss around it. So for the arithmetic mean, we are just adding all the individual values in the data set for ungrouped data, and then dividing it by the total number of values in the data set. So that's just what the arithmetic mean, the formula for the arithmetic mean is. But for the grouped data, because you're having categories now, so you are taking, and each category will have the number of values that are in that category. So to have the number of values in that category, so you have to account for it. Then for the X there in the formula, you are looking at the midpoint of that class interval. So this is the formula for the mean for grouped data, summation F of X all over N, where F is the frequency of each of the classes or the categories, and X is the midpoint of the class intervals. And N, which is summation F, is the number of observations in the data set. So this is an example. You can see it's pretty straightforward. Then for grouped data, so this is the categories of the variable. So you can see now we are not working with the individual values. We are working with the categories now. So for this variable, protein intake, the categories there, you can see the values in category 15 to 24, 25 to 34, just like that. You can see the frequency, which is the next column. So we have, so we have F, which is the number of families. So that's the frequency F. Then for X, we'll take the midpoint of the class interval. That is 15 plus 24 divided by 2, 25 plus 34 divided by 2, just like that, as is shown here. Then you now do F of X, that is the frequency times the midpoint of the class interval. The sum of that, which is in this example is 1,880, is the summation Fx, which is numerator. Then the total number is 40. So 1,880 divided by 40 is your, that's 47 gram, is your mean for this grouped data, right? So that's basically it. One of the key advantages of the mean is that it uses all the values in the data set. That is for ungrouped data. It uses all the values in the data set in this calculation, right? But a disadvantage is that, sometimes when you calculate the mean, you can have decimal places. And then for discrete variables, decimal, of course, that discrete variables, if you remember our first class, discrete variables do not have decimal places of fractions, and it can be the interpretation is not will not be appropriate. For example, number of children. So you have like, for example, now in this class, if I say I want to take the mean number of children, so whoever it is that has a child or has children, right? We now do a mean. So we may have fractions for the mean, which may not be appropriate. So you cannot have 3.72. The mean number of children is 3.72, something like that. So that's just a disadvantage. But however, it is the most useful of the statistical averages. It's the most useful of the statistical averages. And in inferential statistics, it is that's what is used most times. Okay, for the median, it's also another measure of central tendency. That is what it is. It's also another measure of central tendency, and part of the median for small ungrouped data sets, it's best you arrange it in either ascending or descending order. But ascending order is really good because on the left you can easily spot your lowest value in the data set, and on the right you can easily spot the highest value in the data set, right? So it's important to do that. Then in calculating the median, we're looking at the median over 2, and then n over 2 and n plus 2 over 2. In different textbooks, you can see different formula for median position, but it's not too far from this, and you get the same results. So if you have looked at these slides, at least it walks you through how to get the median position, because the median position is not the median. It just tells you the position in the data set where the median lies. Median position is where the median is if it is arranged, right? So that is the what it is. So I assume all of you have looked at these slides, and then with what Professor Maduka has also explained, it's also important to note. So for the slides, you have examples for odd number of values and even number of values. So that's that. For grouped data sets, again, this is just a formula. There are different formulas that you can see in different textbooks, but if you calculate it correctly, it will still give you the same thing. So in this formula, you can see Li plus R over F U minus L. So it's just quite simple. You're looking at the lower limit of the median class. You're looking at the upper limit of the median class, right? Then F is the number of observations, and then R is the number of observations between the last cumulative frequency before the median class and the median observation. So what this means is that looking at the formula, of course, group data, you have your groups, and then you want to be sure to get the, what are they calling it? So you want to be able to find out what the median is for grouped data. But one of the things that you'll be looking out for is to identify what the median class is out of the categories that you have. So in this example now, you want to find out, okay, what is or where does the median lie in this group? So if you're able to identify that, then that is the median.
Even
sorry, so that is the median class. Okay, so calculate the median given. So first things first, we want to find out where the median position is, right? And part of the things that is important for us to do or know is the cumulative frequency. is the cumulative frequency. So how are we going to calculate the cumulative frequency? We will just add the successive frequencies. We will just add the successive frequencies, and that's how we're going to know the cumulative frequency. So that's how we're going to know, or how to estimate the cumulative frequency. I'm a bit fast because I want to believe that I don't know whether I should touch this, but at least I'm just trying to explain since I've already given you the slides, right? So that we can go into inferential statistics. So you can see 5 is the least, is the first of the groups for the frequency. Then you see the cumulative frequency will still remain 5, right? Then we add the next frequency to it. That's 5 plus 19. That gives us 24. 24 plus 10, just like that. So that gives us the cumulative frequency. But aside that, still for the median position, we know that the total number for this that is n for this data set is, if we add it all together, we know that it's odd, right? So the median position where n is odd, how do we know it's odd? Well, of course, we just add everything here now. That gives us 57, right? So n plus 1 over 2, 29th position. So the 29th position is somewhere in this class 30 to 39. Remember, we're not looking at the number, the age group. We're looking at the median position. And we're going to do that from the cumulative frequency. So you can see, as at the end of the second category, that's 20 to 29, we have 24. Our median position, n plus 1 over 2, is the 29th position. So between the 25th position and the 34th position is this class 30 to 39. So definitely our 29th position will be in this third class, 30 to 39. So this is the median class. So now that we've identified the median class, we can now impute everything into the formula and then get our results. So when we say so if we've identified the median class, we can get L and we can get U. That's the lower limit and upper limit of the median class. Ideally, one would just think is maybe you just pick 30 and then 39, but we have to get the true limit. That's why we use the word true limit. So we'll go down to 29.5, and here we go as high as 39.5. That gives us the true limits of that class, right? So that gives us the true limit of that class. Then we have gotten, of course, the frequency of the median class is 10. So that is there. So we have gotten L, we have gotten U, we have gotten F. How do we get R? Look at the definition for R here. The number of observations between the last cumulative frequency before the median class. What is the number of observations between the last cumulative frequency before the median class? The last cumulative frequency before the median class is 24. So how many points from 24 to our 29th position? So that is just what R is about. So the 25th, 26th, 27th, 28th, and then the 29th position. So that's 5. So that gives R of 5. So given this, we cannot impute it into our formula. Don't forget, at secondary school, as in secondary school, even primary, they teach us BODMAS, right? Bracket of division, multiplication, addition, subtraction, right? So you will address the brackets. So whatever it is, you finish with R over F, U minus L, you add it to L. That's the lower limit of the median class, right? So that's what is done in the calculation. So you can see 29.5 plus 5, and that gives us 34.5. So that's just the summary of most of these things. I try to make it as self-explanatory as possible. So when you go back, you can look at it. So the median versus the mean, what informs the choice of whether you are going to use the median or whether you are going to use the mean, right? So if the data is normally distributed, I don't know if Professor Maduka mentioned normal distribution and all that. I'm sure she did. So if the data is normally distributed, right, the measure of central tendency to use is the mean. But if it is not, if it's not normally distributed, that means it's skewed. The appropriate measure of central tendency to use will be the median. Okay, so that is that. Yes, I was saying in different textbooks, there are different formulas, right? But if you apply any formula, you will still get the same result. What we want to see is how you work out the steps, in getting that this thing. If not, yeah, it's some other example. People calculated using different formulas, and they were not wrong. We just look at the steps. Once we know these formulas, right? So my choice of this formula was, I felt it was easier to remember, easier to understand. But if you see any other formulas in any textbook and all that, please go ahead. It's fine so far as, because if you apply and you calculate correctly, you will still get the same answer, whether is it for grouped or for ungrouped data sets. So if the data is not normally distributed, it's skewed, then you will use the median instead, because in data that is skewed, that means you have some outliers, as the case may be, right? The median will be closer to the center than the mean. And there's an example here that tries to show that. You can see here you have 5, 5, 5, 7, 10, 20, 102 as values in the data set. So you can see that we have an outlier here, 102, that tilts the tail of the curve, if we were to draw this curve, to the right. So this is a skewed data because you have this one that is so far off 102 from the other values in the data set. So you can see that this is a tail to right. This is a positively skewed data set using this example. So you can see most of the values are gathered towards the left and a tail to the right. So for this kind of data, so the best measure of central tendency to use here will be the median. Because if you look at the median, it's 7, right? But if you look at the mean, it's 22. So the mean will follow that towards the outlier, right? Because it's large. And remember, we are using all the values in the data set in this calculation. So in this example, you can see that the mean and the median is so far off. And this is a positive skew because the mean is greater than the median. I'm sure if you had read these slides, you will see some basic examples where we talked about skewed data. The mean is greater than the median and the median is greater than the mode, or negatively skewed where the mean is less than the median and the median is less than the mode, something like that. So that is basically that. For the mode, is neither here nor there. Really, we usually just focus more on the mean and the median, but the mode is also a measure of central tendency. And it's for ungrouped data, it is the value that occurs most in the data set. That's the one that occurs with the highest frequency. However, you can have individual data sets that you can have 2 values with the same highest frequency. That is bimodal, right? But for a data set that has only 1 value in the data set, that's one value that has the highest frequency, that's unimodal, right? So that's that. But if you have multiple values with the same highest frequency, so that's a multimodal data set. Yes, I mentioned that if the mean is less than the median, is a negatively skewed data. So you have a tail to the left, right? So in the curve, and the curve. So when we talk about normal curve, we talk about the properties of the curve. But once you start tilting, towards the right or towards the left, you are having a skewed data, and that will affect the choice of the measure of central tendency that you will use. So why would is it that you have not, you guys you do not have this slide? I've shared it a long time ago. Yeah, I've shared this slides a while ago. Somebody saying that they have it. Okay, so that's about that. So most times we don't use the word say there's no mode, right? We say there's no mode. We don't say the mode is 0 because 0 can be a value. After all, if you give a test over 10 and somebody scores 0, it's a score now, right? So when we say what is the mode, you will not say the mode is 0, right? You say the mode, there is no mode. And that is if that value in the data set, if that data set does not have a mode, you say the mode is, there is no mode rather than saying the mode is 0, right? Because 0 can be a value. So it just depends on the terminology, right? So the modal, but for grouped data, the modal class is the class with the highest frequency. Okay, so this is just an example here. So you can see here, there is no mode in this example because all the values in the data set occur singly. All the values in the data set occur singly. So there is no mode that each of them appear only once, right? So that's about that. Then you can see other values as well, other examples as well. Okay, so for the mode for the grouped data, it's even more straightforward than that of the median. Of course, you have your true lower limit, you have your true upper limit. So we're just trying to get to the true boundaries of those values. So that's how we do it, right? That's how we get the lower limit of. So it's to identify the modal class, just as we did for the median. We identify the median class. Told you how to do that. So for this, for true lower limit, true upper limit of the modal class. And what
Take
we
the
say the
back door.
modal class is the class with the highest. So we say it's the class with the highest frequency, right? Then you just do the frequency of the modal class minus the frequency of the preceding class, frequency of the modal class minus frequency of the succeeding class. So basically that. So in this example now, we can already identify the modal class. It's 20 to 29 because it's the class that has the highest frequency. Then to get LD1, the frequency of the modal class minus the frequency of the preceding class. So that's 90 minus 5. Then D2, the frequency of the modal class minus the frequency of the succeeding class. That's 90 minus 10. You have gotten your D1, D2. True lower limits of the modal class. So we for instead of just saying 20, so where does 19.8 fall? Where does 19.7 fall? Right? If you are able to, if it's a variable now that is not discrete, if it's a continuous variable. So most times we take the true limit to 19.5, and then that's the true lower limit, and then the true upper limit to 29.5, at least to accommodate variables like this, if it's a continuous variable. But this example is a discrete variable, so this is easy to just, do. So that's basically that. This is even more straightforward than that of the median, right? So that's basically that for. So that's basically that. So practical calculations. I thought you said Professor Maduka gave you practical calculations. And then we have some here. For those of you who have the slides, which I believe, we had some examples as well. Okay, it's not here. Oh, sorry. Oh, maybe I didn't put, but at least the examples in the slides. Anyway, I can always share. That's not a problem. I can always share practical classes and practical examples that you can work with. I thought I had some in these slides, but obviously I was wrong. That's not a problem. And there are thousands of examples that I can share to you that you can practice and practice till thy kingdom come. That's not a problem. Okay, I think it's the measure of dispersion that had practical exercises, but it's fine. Okay, so which of the measures of central tendency are we supposed to select? I think I've already touched on this. If the data is skewed, the mean may not be suitable, so you use the median, whether it's positively skewed or negatively skewed. And I was saying that if it is positively skewed, that means the mean is greater than the median and the median is greater than the mode. So if it's MCQs, this is where we normally confuse you. In a positively skewed data, A, the median is less than the mean. The mode is greater than the median. The median and the mode are equal, just like that. So of course, if the mean is greater than the median, that means the median is less than the mean. So it's just to play around with English and just confuse you if you really understand what it's saying. Because of course, in a positively skewed data, the mean is greater than the median. So that means the median is less than the mean. And then the median is greater. So if the mean is greater than the median, it's greater than the mode. So that means the mode is less than the mean. The mode is less than the median. That's what it means. The mean is greater than the mode. So we just do that to just confuse you a bit if it's MCQs. As far as I'm concerned, if it's basic statistics or descriptive statistics, it should not be such an issue, right? Any question you see, you should be able to attempt. So that's basically that. I've talked about the mean, all the for ungrouped data, we use all the values in the data set in the calculation of the mean, right? For group data, we'll take the frequency of the class and then get the midpoint of that class, then multiply them together and then add it to now form your numerator. So basically, this was what I was just trying to explain, right? So if the mean is greater than the median and the median is greater than the mode in a positively skewed data, that means the mode is less than the median and the median is less than the mean, right? But in a symmetric distribution, that's a normal distribution, the mean, the median, and the mode are equal. So when we get to introduction to distributions, we'll talk about that. But let's just touch a little on measures of position. I expect that you should have read this, so that this is just to revise, and then I'll send some practical questions across. So we're talking about measures of central tendency. Let's look at measures of position. So for measures of position, we want to see what position a value in the data is relative to others. So that is what the measures of position tell us. So you have the percentiles, right? You have the deciles, and you have the quartiles. You have the percentiles, you have the deciles, you have the quartiles. So each of these percentiles are all values. They are all values. So that is what it is. So when we talk about the measures of dispersion, we'll talk about quartiles. But here, let me just show you the percentiles. So the percentiles are not percentages, because 70% may not be the 70th percentile, right? So that is clear. In percentiles, you are just trying to divide the data set into 100 equal groups, and you have 99 percentiles that do that. So percentage, person says 72 over 100, person got 72%. But what is that 72% relative to other individuals in the class? 72%, the person may have scored better than 2% of the class, or the person could have scored better than 99% of the class. So that is the interpretation of what the percentiles mean. So how do we calculate this? You arrange the values in the data set. You find the number of values that are below that value that is of interest to you, add it to 0.5, divided by the total number of values, multiplied by 100. So we're using 100 because we want to now know what is, of course, when we talk about expressing it, we are just trying to say that we want to now know what proportion did you score better, what proportion of the class did you score better than, so that is the essence of the percentile. Okay, so let's see an example. So it here gives a 20 points test to 10 students, scores are shown. So what is the percentile rank of a score of 12? So you're just asking how many people did This is your score of 12. How many people did you score better than? So as much as possible, any data, so far as it's ungrouped data that you are giving, please kindly arrange it, right? Arrange it either in ascending or descending order, preferably ascending so that you're not confused, so that you just have the lowest value in the data set. Since most of our writings is left to right, so that you just know that to the left, you're seeing the lowest value in the data set, and to the right, you're seeing the highest values in the data set. So arrange it. Find out the number we're interested in is 12, right? The score. So all the values below 12, we have 6 in number. Add it to 0.5, divide it by the total number, and then you get the percentile. So we got 65, that's 65th percentile, right? So that means the person who scored 12 did better than 65% of the class. So that is just what the percentiles tell us. So there are 99 percentiles that divide the data set into 100 equal halves, and it tells us a measure, it gives us a measure of the position. For deciles, we have 9 deciles that divide the data set into 10 equal parts. So you can see here, by the time you get to D5, 50% of the values in the data set, that is after arranging in for ungrouped data sets, 50% of the values in the data set are below D5 and 50% are above D5. So D5 corresponds to the median. So D5 is also the median in a data set. So this is another question that pops up pretty regularly. So the following is true, or following are true. D5 is equal to the median. And the median is Q2, that's the second quarter. So if we have D5 that separates the data set into 2 equal halves, right? The median does that same work. And then the 50th percentile does that same work. So D5 is equal to P50. D5, that's the 5th decile, is equal to P50, that's the 50th percentile, is equal to the second quartile, that is the median, right? So that's another way we just tend to play around this data set. Okay? So this formula for calculating the deciles, nothing much here, is pretty easy. So again, arrange everything, just arrange everything so that you don't get confused in ascending order, or any value, anything that they give you, just arrange it in ascending order so that you don't get confused. Because if you don't arrange it, you may get another value when you calculate. So you can see here, it is pretty straightforward. So find D5, they say find the 5th decile for the following set of data. Arrange it as you should. So I is a decile to be calculated, N is the number of values in the data set. So if it's a 5th decile, I will be 5, then N 50. So this is pretty straightforward. Just divide it. You see, you have the A. So in this calculation, you are looking for the position where the 5th decile is, or whatever decile it is that they tell you to calculate. So you can see here we have calculated 8. So it's the 8th position. So by the time you now count, you now see that your 8th position there is 10. So your 5th decile is 10. Don't forget that all these numbers are saying 5th decile and 59%. They are all values in the data set. It's just for you to now in the data set. So that's that. I will just take maybe 1 or 2 questions so that we can move to measures of dispersion. Yes, Dinda Dauda, I can see your hand. Is it a question? Is it a comment?
Yes, good evening, sir.
Yes.
So my question is, when do we use the mode?
So the mode is a measure of central tendency, and most times for categorical data, you just want to know, okay, or which of these which of these groups or which of these values, have the highest frequency. But generally, most times the mean and the median. Most times, the scientific writing that we are really interested in, right? Out of these 3, the mean, of course, is the best measure if the data is normally distributed because it uses all the values in the data set. So for mode, mode is, it's not as if it's not important, but it's not really used so much, unless maybe you really want to report maybe something it has the highest frequency. Sometimes in categorical data set, you can say, okay, so number of people are in this group, or so number, so we can say, okay, the modal class or the modal, but rarely we use it in scientific writing per se. Most people will just report it at the mean or the median, depending on whether the data is normally distributed or not. Most of the scientific papers, is they report it at the mean or the median. Most times they report the mean, so far the sample size is large, and because most times if the sample size is large, I don't know if she talked about the central limit theorem. Sample size is large based on those assumptions.
Yes, she did.
Most people just report the mean and the standard deviation. Remember, I also talked about the fact that you usually don't report the measure of central tendency alone. You report the measure of central tendency and the measure of dispersion. Okay? Yes, Ugochukwu. No, the measures of dispersion, sorry, let me just address this question. The measures of dispersion and measures of position are not the same. The slide suggests that. Yes, Ugochukwu, sir, please go on.
Good evening, sir. Can you hear me, sir?
Yes, I can. Go on.
Yes. There was this, I don't know if it's in the mean or the median, the formula where we had the R over F. I didn't understand what R and F meant.
Okay, so R, I said, is the number of observations from the number of observations from the cumulative frequency of the preceding class. That's the class before the median class, right? The number of observations from that cumulative frequency to the median position. In that example, we said the median class, the median class was the third class, 30 to 39. So we had 10 to 19, we had 20 to 29, we had 30 to 39. We identified from the median position that the median class was 30 to 39, right? And then the first two classes, that is, we had the first frequency of 5, the next frequency of 19. So the cumulative frequency as the second class is 24. So R is how many observations from 24 to 29, which is our median position, from the 24th position to the 29th position. So that's 5. So that's how we got R of 5. Then F, of course, the frequency of the median. So that is how we got R. If you read the slides, it's pretty self-explanatory. Okay, the last, Adaku Waniru.
Good evening, sir. Thank you very much for your lecture. Please, I don't quite understand the relevance or where percentiles and deciles are to be applied. And if you can just go through them again, please. Thank you so much, sir.
So we just, most times you see all these examinations that people write. It's not a pass, all these very high standard organizations, right? That very high standard examinations that people write. So you may get 70, but they'll tell you that, sorry, you didn't meet this thing. Most of those things they do is percentiles they use. You can score 80 or 100, but you didn't meet up the percentile that they've set for themselves. Right? So all these foreign exams and all those things, most times it's percentiles that they use. So you may score very high, but you may not be selected because it's percentile. So they are just interested in the top 5%. They're interested in the top 10% of the class, right? So they use the percent, they just calculate what is the percentile. So we take that percentile as the pass mark. So that's the application in a way. That's the application in a way, right? But like I said, that's why it's a measure of position. We want to know what that score is relative to the other members of the class. So somebody who scores 80 over 100 will be happy. You have blasted, you are high. In our normal, this is A now, right? But let's say you want to now go and write all these foreign exams, and I'm not saying they don't even do that in Nigeria. They may do for very high standard examinations. They will just calculate the percentile to find out what is that your 80 that you scored. You did better than how many people in the class, or how many people did better than you. But if they are interested in that's why most times all those people that they take the best of the best. It's not because you have scored very, very well, but that percentile, they want to find out what that percentile is. So if that percentile is 90, so they can just say they are taking the 90th percentile. They may not tell you. They may not tell you, right? So that means that you did better than 90% of the class. And then they put their score there as the pass mark. So most times, for some of these examinations and all that, they're not interested in 50 cutoff and all that. They just look, okay, and they now choose the score that favors maybe 90th percentile, 95th percentile, 80th percentile, whatever, and just note that as the pass mark. So that's the relevance. You can have it. So that's more like practice, But if you're interested in that kind of thing or assessments or all that, of course, percentiles come into play. It's just a measure of position. Of course, we don't see it usually in articles, journals, and all that. We may not see it so much in all this. But most of these foreign examinations, what determines their pass mark is not 50, it's a percentile mark. So that's why you can get 75, but they'll tell you that, sorry, you did not meet up. The standard was so high, and you did not meet up, and all that. Okay, I think that's that. This is a new hand. I'm sorry, I won't entertain that. Let's move on. We have so much to talk about. Okay, so Amaka, you can type your questions in the chat box. So I'm just going to review the measure of dispersion quickly, and then we will continue from there. So the percentile, so standard normal distribution and all that. I'll get to that, but that really does have. It's not really the same as percentile because we're working out these standard normal distributions in terms of the standard deviation and the standard error. So there are slight differences to it, and we're working it out as proportions, not as percentiles. So don't get it confused. It's just small differences between there. The concept is a bit different because we're working out proportions under the curve using the mean and the standard deviation, or the mean and the standard error, depending on what you're looking at, right? To get the proportions under the curve. It's proportions, not percent. Okay, so let's go to measures of dispersion quickly. So measure of dispersion, we usually don't report only the measure of central tendency. We also report the measure of dispersion as well. Right? So that's why you see anybody that's reporting the mean, the standard deviation will also be reported. If you're reporting the median, you report the interquartile range, something like that. So that is it. But in the measure of dispersion that we'll be looking at today, we're talking about the range, the interquartile range. I think I need to change this. The interquartile range, the quarters in themselves are measures of position. But somehow we will calculate the quarters before we now talk about the interquartile range, right? So that's that. Then we have so let me also edit this a bit. Variance is on its own, standard deviation. It's just that they are very closely related to each other, right? So range, interquartile range, variance, standard deviation, coefficient of variation. If you've read this, I'm sure at least So if you've read this, you will say you will know. I think you see how what the measures of dispersion tell us. It just tells us the how far away the spread of data set. Okay, so let's go to somebody's in chat box saying this, but scoring high in a particular exam doesn't count during percent. Of course, yeah, that's what I said. It doesn't really count like that because they can just place their cutoff based on the percentile rather than on the score. Okay, so let's go to the range. I've talked about this. You can read that. Range is just the difference between the highest value in the data set and the lowest value in the data set. Remember I said that any data that's given to you on group data, just try as much as possible to arrange it before you attempt it. Because if you don't arrange it, they may just say calculate range, and you will just go and you will just pick the two extreme values. Meanwhile, that is not the highest and that is not the lowest value in the data set. So it's important to note that. Disadvantage of the range is there, and the range doesn't use all the values in the data set. So that's a disadvantage. It just picks the difference, just picks the highest value and picks the lowest value. So that's about that. I will not dwell on this. It's very easy. You have the slides, go back and look at them. For the quartiles, remember, we talked about percentiles, deciles, quartiles, but we didn't see quartiles in that slide because I put it here because you calculate the quartiles before you calculate the interquartile range. So there are 3 quartiles. Remember, there are 9 deciles, 9 deciles that divide the data set into 10 equal parts. You have the percentiles that divide the data into 100 equal parts, 99 of them. And then you have the quartiles, 3 of them. That's Q1, Q2, Q3. So to calculate this interquartile range, they're just calculating medians. So the median of the entire data set is Q2. So of course, if you have a group data, you arrange them, and then you calculate the median. So that gives you Q2. Then all the values in the data set below Q2, you arrange that you get them all out, calculate the median of that first half. That gives you Q1. Then you calculate the median of all the values in the data set above Q2. That gives you Q3. So Q3 minus Q1 is the interquartile range, right? So you're just calculating 3 medians. The overall data set, that's Q2. All the values to the left of the data set, you calculate the median of those values, that's Q1. All the values to the right of Q2, you like Q3. So Q3 minus Q1, that gives you the interquartile range. So if you have the slides, I'm sure you should have seen this or looked at this already. So you can see Q1, Q2, Q3 dividing the data set into 4 equal. So this is another what proportion of values in the data set lie between Q1 and Q3? What proportion of values in the data set lie above Q3? What proportion of values in the data set lie below Q1? Things like that. We just confuse you. Just this slide alone answers all that. You can see all the proportions, that, so this Q1, Q2, Q3 divide the data set into 4 equal halves, right? So all those scenarios are painted. Just this slide alone gives you a clue to answering all of them if you understand what is really happening. So first quartile or lower quartile, that's Q1. Median is the second quartile or middle quartile, that's Q2. Third quartile, upper quartile, that's Q3. And I've told us how to do it. how to calculate each of. They're just calculating medians. That's basically all that you are calculating. Okay. Okay, so let's continue quickly. So I think I've talked about this. So you see the slides and you can see the examples. So this is the entire data set. We have the same process we learned from measures of central tendency, how to calculate median. It's still the same thing. Calculate the position, pick out the values. So this is the overall median. So that's Q2, which is 240. Then you take all the values to the left of the data set of Q2. So you arrange them, calculate the median of it, right? That gives you Q1. You take the values to the right of the data set, you calculate the median of it, that gives you Q3. Q3 minus Q1 is the interquartile range. Again, arrange the data. If not, you'll be calculating wrong figures. If you use it as it is, you are calculating wrong figures. So I always arrange the data. So first you have data sets, arrange them first before you do anything, whether it's although mean you may not necessarily need to arrange because you're using all the values in the data set. But I would say that just arrange, just in case there's a follow-up question, calculate median. It's not that time you start rearranging because exam situations, if you are tense, you're just calculating and you don't arrange first, you've calculated mean and the follow-up question says median. You may forget to arrange. So once you just have it, just arrange it first in ascending order before you go ahead to do anything, even if it is me, right? So that you don't get confused. So these are examples is there. Then in the quarter range is just Q3 minus Q1. Don't forget the quarters themselves. To get the quarters themselves are measures of position. It is the interquartile range that is the measure of dispersion. But I just put it here because I didn't want to detach it. You definitely you get the quarters first before you calculate interquartile range. You know. Okay, so now to variance and standard deviation, which is very, very important in inferential statistics. So what this means is that we are trying in calculating the variance or the standard deviation, we are looking at the distance between an individual value in the data set and the mean. So that is what we're looking. So that is what we're looking at. How far away is an individual value from the mean of that data set? So that is the mean deviation. And it's expressed as the individual value minus the mean of that data set. Why it is squared is that some values may be above the mean, some values may be below the mean. So if the individual value is above the mean, of course, you have positive values. But if the individual value is below the mean, you will have negative values, right? So squaring it just takes away all those negative values and all that. Then you sum the squared deviations of the mean. That gives you the numerator, right? Then we divide it by n minus 1 because we are taking samples. So we are taking samples from that population. Remember, most times we are not dealing with the entire population. If we're dealing with the entire population, our denominator will be n. But we're saying n minus 1 because we want our variance to be a close estimate of what the population variance will be. So that's just some statistical jargon that explains the denominator. But if we're taking each of the individual values from the entire population, our denominator will be n. But most times we are not working with the entire population, we're working with samples, so we're going to subtract 1 from it. That's just the statistical language. All in all, we're trying to say, okay, the best estimates of the sample variance from the population variance represented by n minus 1. So variance and standard deviation are closely related because the standard deviation is the square root of the variance and the variance is the square of the standard deviation. So this is another place that we try to confuse in MCQs. The following is true. A, the square root of the standard deviation is the variance. The variance is the square root of the standard deviation. The standard deviation is the square of the, something like that. We just try to confuse you. If you know what you are doing, you know what you are doing. So the standard deviation is the square root of the variance, while the variance is the square of the standard deviation, right? And is the best measure of dispersion, right? And widely used in calculation. Just like the mean, the standard deviation uses all the values in the data set. Same thing with the variance. So that's why they are closely related, So the standard deviation goes with the mean. So if you're reporting the mean, you will report the standard deviation. So that's why if you look at figures, they are reporting anything they are reporting mean, they are usually reporting the standard deviation, right? So that's that. And then the mean and the standard deviation are the measures of central tendency to use when the data is normally distributed. But the median and the interquartile range is the measure of central tendency and the measure of dispersion to use when the data is skewed, whether to the right or to the left. Because I asked this question for one set like that. Can't remember whether it's School of Public Health or generic maths. I can't remember what, but I asked. So the question was calculate the mean and the median. I gave a data set and I said, calculate the mean and the median. I expect you to calculate the mean. I expect you to calculate the median. And I said, looking at the result of your mean, I was even given all the clues. So I said, looking at the result of the mean and the median, what calculates the measure of central tendency and the measure of dispersion? That you should calculate the appropriate measure of dispersion to use. And I put in brackets, hint, look at the mean and the median. For the question, the mean was way larger than the median. So already that tells you that it's a skewed distribution. So in statistics, just understand the principles and you are home and dry. But if you are just the cram type in statistics, because my questions will most often be applied, I'll not be giving you define this, tell me this, right formula. No, I'll be giving you applied questions because that's the true test of whether you understand the principles behind it. Because now there are so many statistical formulas, so different statistical softwares. Nobody expects you to be calculating so many things with head cramming formulas. Nobody expects you to do that. There's SPSS, there's EpiInfo, there's Stata, there's R, there's Python, there's this, there's that. A click of the button gives you mean, median, mode, variance, interquartile. It gives you everything, statistical test. But it's the interpretation that sets you apart. Anybody can press anything and result will come out. But it's interpretation. So I test the interpretation of what you know. So I told them calculate, I gave 20 figures or 20 results or something like 25. So then calculate the mean and the median. It was a skewed data. Median was markedly large. Of course, in real life situations, when we say mean, median, and mode are equal, we'll see it in normal distribution. It doesn't necessarily mean mean is 25, median is 25, mode is 25. Of course, if you see a mean of 25 and a mode of 24.8, it's almost the same thing. It's almost equal, right? But if you see mean that is 25 and median that is 39, of course, it's far off from each other. So it's most likely that data is skewed. So this is the reasoning. So I told them calculate mean and median. I think the mean was a value, the median was the mean was way greater than the median for that data set. And I told them calculate the appropriate measure of dispersion. Calculate the appropriate measure of dispersion. And I put hint. Look at the results of A above. That is the mean and the median that you have calculated. A smart thinking person will see that the mean is greater than the median and work out the interquartile range. But a lot of the students were calculating standard deviation. So I was like, they don't understand. And I gave hints there. Look at the mean and the median. That tells you that data is skewed. Then I said, make a note on the distribution from all that you have calculated. What I wanted, just a simple line there. It is a skewed distribution because, and give reason. So that was the way I put it. So all I wanted for them to say is that it is a skewed distribution because the mean is greater than the median. Full stop. But most of them were saying all sorts of things. It was a business, it's bimodal, some say it's multimodal, this, that. They were just speaking English because it was on the slide, right? So simple thing that turned out that it was so difficult. I was like, it was not difficult if you understand the principles. And it was a small data set, so that was it. So that was, at that time, right? So what am I saying? Again, you report the mean and the standard deviation if it is normally distributed, or you report the median and the interquartile range if it is not normally distributed, that is if it's skewed. Of course, the central limit theorem tells us that if the sample size is large, you can argue that it will still follow a normal distribution with sample size is large, right? So that's why most times if you have large sample sizes, you can still go ahead and report your mean and your standard deviation. It's fine, But if you have told us, right, you are going to do, results, people will say, oh, they will do test for normality, they will do this, they will do that. No problem. Do your test for normality and report the appropriate thing, So that's basically that. Okay, so this is the formula for standard deviation. This formula for standard deviation. So you can see that's why we say the standard deviation is the square root of the variance. So that formula for variance, we have just put the square root sign there, right? So if we square this, that square root sign is off. So we have the variance. So the standard deviation is the square root of the variance, and the variance is the square of the standard deviation. Because if we multiply this by each other, the square root sign just goes off. So the formula left and right is the same, but you can see that we're using the notations for population, the population parameter on the left, while we're using sample parameters on the right. And that's why the denominator has changed, because once we have taken samples, of course, we've introduced errors and all that, but you can see it's almost the same, right? And we're using notations, like look at the population mean and look at the sample mean. We're using the notations for the population parameters on the left. You get, so that's that. For grouped data, it's almost similar to what we saw for the mean, for the standard deviation, and even the variance. We're introducing the frequency now for each of those classes. So that is for grouped data, right? Don't forget that the mean, of course, we need the mean now. So for group data, you are calculating the mean for that group data, right? And the formula, remember it and all that. So we're looking at the frequency of these classes, right? So this is if we're looking at calculating for grouped data, you can see the class intervals or the class groups. You can see the frequency there, So to get X now that we're going to use for the formula, still the same thing. You are doing the midpoint of the class interval. And then the other calculations will follow according to the formula. So that is that. So this is for ungrouped. You can see the examples there, so you can go back and look at it. Then for grouped data, I think I put it as a practice exercise, so you can go back and so this was a slide I was referring to that I put practice exercises, so you can go back and look at it. But let me just talk about coefficient of variation. So we've talked about all these other ones: range, interquartile range, variance, standard deviation. For coefficient of variation, this comes in when we are comparing in sets of data that are not measured in the same units. If they were measured in the same units, the standard deviation would have just been best to compare the two sets of data. So, for example, I'm interested in saying if the weights of males and the weights of females, which of these data sets have greater variability in the spread of their weights? Is it the males or is it the females? both weight and the variable weights in both males and females is measured in kilograms. So same unit, I will just calculate the standard deviation of the weights for males, the standard deviation of the weights for females. And anyone that has the highest standard deviation, it has the highest variability in the data set. But if I'm comparing weights in one, I have weights as one data set and I have blood glucose level as another data set. Of course, these are two data sets that are measured in different units. One is kg, one is millimole per liter, right? And I'm saying, okay, I'm trying to think which of these data sets has greatest variability. I will instead use the coefficient of variation because they are not measured in the same unit. So in this data set, I'll calculate the coefficient of variation, which is standard deviation over the mean times 100. I get the value. I go to this blood glucose data set, calculate the standard deviation and the mean. So whichever has the highest coefficient of variation has the highest variability. But if they are measured if those two data sets are measured in the same units, just go and use the standard deviation. So that's the concept of this coefficient of variation. So that's that. For those who was asking, someone was asking about practice exercise. C13 for you is go back and look at it. If it's for measures of central tendency, I can send thousands of questions for you. So I'll just take a few questions and then let's see, we can do introduction to this thing and then we see where that goes. Yes, Shedrack.
Good evening. Thank you. I wanted to ask a question. While you were teaching, when you got to the part for, you were like describing a practical scenario for exams. You said when you would look at, you give a data set or data table where the mean and the median, there's a significant difference, and then you expect us to know if you are going to use standard deviation or the interquartile range. I want to ask if there's a particular degree of skewness you would expect before you would want to switch, or is it once you notice that once it is no longer equals to once the mean and the median are no longer equal to each other, even if it's like -1 or +1, then we have to switch. Thank you.
Okay, so I'm not going to I wasn't really particular about that, but I made the question in such a way that there was a marked difference between the mean and the median. You get, I was so that anybody, if you calculate it correctly, you know that the median was so far away from the mean, right? To tell you that it was a skewed distribution. You get, if the median and the mean were so close to each other, maybe 1 or 2 units, that is it will be, it's possible that it could be normally distributed and you may not be wrong, right? But in that scenario I painted, I put the median was far away from the mean, right? So it's just for you to interpret mean greater than median or median greater than mean or whatever, and just interpret it as a skewed distribution, and then you work it out according to the other questions. So the principle of that question was to test whether you know part of the measures to determine whether a data is normally distributed or not. So one of the ways is to look at the mean and the median. Are they close to each other or equal, right? If they are, then you can say it's most likely normally distributed data. Another way to look at it is look at it graphically. Look at the histogram. So look at the shape of the histogram. Does it follow that bell-shaped curve? More of the values towards the center and a few at the tails towards the end. Look at the shape of that curve. If it gives you the bell shape, you can superimpose a curve on it. It gives you that bell-shaped curve, most likely a normally distributed data. Then you can now start going higher, skewness, kurtosis, and then your test for normality. There's also hypothesis test that you can test to see if the data is normally distributed or not. So that's your Kolmogorov-Smirnov or your Shapiro-Wilk test. So you now interpret it accordingly. But I'm just simple ways to know. Look at the mean, and these are measures of central tendency first. Well, as we are going to this introduction to distributions, you see one of the key, if almost like the number one, mean, median, and mode are equal, right? So mean, median, and mode. But if you now want to now start writing plenty things, tell us, oh, you shape of the distributions, common gross Smirnov, skewness and kurtosis and blah, 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 blah. For me, the simple things first before you start going to go and, look at all that. But for research purposes, some people just tell us that they'll do a test for normality and all. No, it's fine and good. The essence with the research is that what do you want to do? Did you do it? You tell us that, okay, I want to test my data for normality, no problem. Okay, what did you do to test for that normality? So you tell us if that's what it is you want to do. But don't forget as well, the central limit theorem as well also plays a role, particularly if the sample size is very large. So that's about it. I hope I've been able to answer your question.
Yes, sir. Thank you, sir. Thank you, sir.
Okay. So someone is asking, is the coefficient of variation is it the same as standard deviation? You don't hear anything, everything I said. I said standard deviation is different now. Why are we listing it separately if they are different? Or if they are not different, why are we not listing them separately? So the coefficient of variation is different than the standard deviation, and the calculation is not the same. You need the standard deviation to calculate the coefficient of variation, because that formula I gave was standard deviation divided by the mean times 100, right? That's that. But the standard deviation, we have seen the formula now. We have seen the formula, so they're entirely different. If they're the same unit, the two different data sets, the variable of interest is the same unit. Just calculate the standard deviation in this data set, calculate the standard deviation in this other data set, and that's fine. Then whichever one has the highest standard deviation is the data set that has the greatest variability. But if these two data sets, the variables of interest are different and they are measured in different units, that's when you use the coefficient of variation. Okay, so some of these questions, the answers are all on the slides. Yeah, all on the slides. Someone say, I don't understand the best measures of dispersion when the mean is greater than the median. And I've talked about this, so please go and read the slides again. What is quantile? I never said anything about quantile. I said quartile. I don't know what you mean by quantile. Quantile and quartile, but we talked about quartiles, we talked about interquartile range, we talked about percentiles, we talked about deciles, Okay, so I don't know where you're getting that. Amara, but I think that's the last question we'll take, so we can go to other things. Sorry, I know I postponed a few of my classes in the past. So many things happening all at once. Amarachi.
Okay, good evening, sir. Good evening, colleagues. Okay, sir, please, I wanted to ask a question. For this skewed distribution, where we use measures of dispersion, is it necessarily the mean being greater than the median, or it can be the median greater than the mean also?
So it shows that you people have not read this. Everybody's give me slides, give us slide before the class. This one, you've had these slides for more than, is it more than a week? That means you didn't read it. I said, if it is, we say normal distribution, the mean is greater than the median. I'm sorry, for normal distribution, the mean is equal to the median. For positively skewed data, that's the tail to the right, the mean is greater than the median. For negatively skewed data, the mean is less than the median. It's on the slides. So if we say positively skewed, the mean is greater than the median, and the median is greater than the mode, that means the mode is less than the median, and the median is less than the mean. Abi, if A is greater than B, that means B is less than A. Is that not so?
Yes, sir.
Yeah. So, so that's that. The answer, this question you asked me, is on that slide. Maybe you have not read it or even seen it in the first place.
I've seen it, but I've not read it.
The truth is coming out.
Thank you, sir.
Okay. Okay. Everybody has greater variability after calculating the variance. Some common questions where on they ask me now, wow, say how do you determine the value that has the highest variability? If you calculate coefficient of variation for data set A and you get 20%, and you calculate coefficient of variation for data set B and you have 30%, which one has the highest coefficient of variation? This kind of questions people are asking me now. The 30% is higher than the 20 now. So that one has the highest value and has the highest variability now. No. Okay, so introduction to distribution and the normal distribution. So Professor Monica has already talked about some of these few things. So let me just put a bit more context to it, so that if she has covered these areas, fine and good, is revision. If she hasn't, you learn it as well. So we'll start with that. Okay, so introduction to this. So in distribution, when we talk about distributions, what are we really talking about? Just the occurrence, the pattern of occurrence, how repeated the values are in the data set, right? So that is what this distribution is all about. So the pattern of occurrence of the values of a variable in a data set. So that is what distribution is. So you can have frequency distributions, you can have probability distributions. For frequency distributions, we're just saying that, okay, how many people scored this? If it's a test, for example, how many people scored this? How many people scored this value? How many people scored 70? How many people scored 60? Something like that. So you have the frequencies of these individual scores, right? So it's a collection of data, scores, and all that, right? But in statistics, we are more or less interested in probability distributions. So if we can say what are all the possible values, or what are all the possible scores that somebody can get in a test, then we can be able to now make some probabilistic statements about where we think a score will lie. So that is the context of this, right? So thus the distribution of an event consists not only of the input values that can be observed. So for example, you have 90% of the class, okay, let's say you have a score, a test scored over 10, 90 people in the class, 89 of them scored 10 over 10. One person scored, say, 8 over 10. But 8 and 9, should we say, what did I say? 89% scored, say, 10 over 10, yes. And then one person scored, say, 9. So for the fact that all of the people in the class scored 9 and 10 does not mean that 9 and 10 are the only scores that can come out of that test. You can have 0. Somebody will not. It's possible that somebody can score 0. It's possible that somebody can score 1. It's possible that somebody can score 2. So all the possible scores that can come out of that test is between 0 and 10. That's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know all the possible values. Doesn't mean that somebody scored 1 or somebody scored 0. But we know all the possible values that can come out of that test. And once we know that, it's possible to now say, okay, what's the probability that somebody will score 5 in this test? So that is the concept of the probability distribution, right? So that's that. Then we have different types of distributions. Is it normal? Is it distribution, binomial, chi-square distribution? So many distributions. But the one that will really be of importance to us is the normal distribution, because most of the variables, follow, most of the variables in nature and all that follow this distribution with the characteristics that we shall see, later, or that you may have heard from Professor Madison when she taught your class. So that's that. So that's why it's called normal, because they found out that most of the variables in nature can follow this distribution. It was so normal, so they called it the normal distribution. Although it was discovered or named or described by somebody called Friedrich Gauss. So that's why they also call it the Gaussian distribution. We shall get to that. Then for, of course, absolute frequency, relative frequencies, and all that. So in a frequency distribution table, you have the frequencies. But if you express those frequencies as percentages, you have relative frequencies. Then you have the cumulative frequency. Of course, you're just adding the successive absolute frequencies or the successive relative frequencies. So on this, the last column on the right that shows cumulative frequency, there is the cumulative relative frequency. What is missing on this table is the cumulative absolute frequency. So don't forget, we saw the cumulative absolute frequency when we're looking at the median for grouped data. So if we were to put another column, maybe we would have put the cumulative absolute frequencies. So the first number there will be 2, the next will be 11, the next will be 11 plus 28 is what? 39. So that's that. Anyway, this is for measures of data presentation, when you talk about tables and all that. That's not where my interest in. So all these ones are just graphical methods that we can use to explain, that we can use to also talk about frequencies as well, frequency distributions as well. You can see the one on the left is the bar chart. Bar chart we use to represent categorical data, right? Then the histogram on the right, we use it for numeric data. You can see that the bars touch, there's no space between the bar and the histogram compared to the bar chart. So this is just small digression, but we're trying to look at the shape of this, the top left. So this may likely be skewed. You understand? Although this is not an appropriate graph to really discuss that, right? Because this is just showing the category. But look at the histogram. So I was trying to talk about the shape of the histogram. So if you look at the shape, what does this tell you? This is most likely skewed. You can see the tail to the right, right? I know this may not be so appropriate per se, but let's look at the shape of this. You can see that you have a bit more to the left, then some kind of tail that goes down like that. Although this may not be appropriate because it speaks to some other stuff, right? But I just drawing your attention to, it's not even negatively skewed, it's actually positive skewed, tail to right. So don't give us wrong stuff. So look at the tail. So the tail is where is it because I'm using the word tail? That's a statistical term now. The height of the bar of the bar or the curve, and then where is the tail dragging to? Is it to the right or to the left? This is clearly to the right now. So this is showing a positive skew. Again, like I said, it has not be so, because they're looking at relative frequency, age groups, and all that. But that, I'm just trying to give you an idea of when you see a histogram, look at the shape a bit, and that gives you kind of like an idea. So this is positively skewed and not negatively skewed. So if we were, so that's what I was talking about. If this were individual values now, and we calculate a mean, definitely when we calculate the measures of central tendency, definitely the mean will be greater than the mean. But this is, like I said, what they used to describe this is not so appropriate for that for the discussion. But look at the normal distribution, look at the shape of the histogram. So this is a normal distribution. That's why I was like, look at the histogram. You can see that all the values are more to the center, and then you have the tail, right? Which is kind of what you have on the right is what you have on the left kind of setting. And it's a smooth shape, a smooth curve, which is called bell-shaped, bell-shaped curve. So that is the shape of the histogram. So if you see a histogram like this, most likely tells you that you may likely be dealing with the normally distributed data. So this distribution, normal distribution, is also known as the Gaussian distribution, named after Carl Friedrich Gauss, And then data from many fields of study surprisingly could be described by this distribution. So much so that the distribution is often called the normal distribution because it was so common. Most of the variables, most of the things that they were doing, whether in public health sciences, biological sciences, social sciences, and all that. By the time they measured them, so first was a numerical data, they did all their things and they plotted. You found out that it was almost always following this distribution. So what are the properties or characteristics of a normal distribution? Symmetrical about the mean. When we say symmetrical about the mean, that means the left side is a mirror image of the right side. The left side is a mirror image of the right side. So that's what we talk about the symmetric about the mean. Then the mean, median, and mode all coincide. That's they are equal. We have heard this, I've talked about this, I've said this a number of times. Mean, median, and mode. Don't mind all this English, all coincide. They are equal. Then, of course, if you have a mirror image of each other, left side is right side, that means what is on the left side, the proportion on the left side is also the same proportion on the right side in a normally distributed curve. So 50% of the scores below the mean, 50% of the scores above the median. So this is another place where in MCQs we can confuse you. Because most people, it's just the mean. Properties of the normal distribution, true or false. A, it is symmetrical around the median. Somebody will go and tick false because all their minds is mean. But forgetting that in normal distribution, the mean, the median, and the mode are equal. So in MCQ, you can just put it's symmetrical about the median. Somebody will say, it's mean. You're going to take false. Forgetting that the question is in a normally distributed data. Don't forget the mean, the median, and the mode are equal. I can as well say in a normal distribution, 50% of the scores lie below the mode. I can as well say that. And it will be true because the mean, the median, and so this is how you test principles. Most people just say, it's a mean. But it's in a normally distributed data, we have known, okay, mode is a far-fetched. It's far-fetched because most people, mode is like, well, at least median. We say median. 50% of the values in the data set lie below the median, true or false, in a normally distributed data. There's no catch, there's no anything. It's if you know that the mean is equal to the median, we know in a normally distributed data. So anything that applies to the median applies to the mean in a normally distributed data. Right? So that's about that. Unlike you can see the curve on the right. You can see the curve on the right. So you can see that's a tail to the right. You can see that the height of the curve is more towards the left and you have like a tail to the right. So this is positive skew and the mean. So if we're counting, we look at the values on the x-axis that go from left to right. So you can see that the mean is greater than the median and the median is greater than the mode. So that tells you that that figure on the right, that is, I don't know if I can see my cursor here. This one is a positively skewed data set. Look at the shape of the curve. You can see this is the bell shape and this is a skew data. In particular, positive skew. So That's that. Okay, so in statistics, most times you don't cram or you understand. Then another characteristic is what we call the empirical rule. So 68% of the values in the data set lie. So, of course, don't forget, this normal curve is most likely defined by the mean and the standard deviation, right? And we use it a lot for when we are looking at, so what defines in inferential statistics, what defines everything that we do is the mean and the standard deviation once we're in the realm of inferential statistics. And then to get the appropriate concentrations under the curve, proportions under the curve, we look at the mean and the standard deviation. So key characteristics of this distribution is that 68% of the values in the data set lie within one standard deviation away from the mean. That is below the mean, above the mean. So that's why you see the diagram here. So if it is 68%, that means this half is 34, this half is 34. That makes it 68. Then 95% lie within two standard deviations away from the mean. So you can see, so that means here gives us 95. So if we have 68 here, we have 27 remaining. So of course, symmetrical about the mean. This side will be 13.5, this side will be 13.5. So you have 13.5, 34, 34, 13.5. I think that should be it, and that gives you 95, right? Then 99.7% of values fall within three standard deviations away from it. Actually, this 95%, by the time we get to this thing, we will explain more. So this is just an empirical rule. So with this, we can get proportions under the curve, at least that may account for this, right? So if we say the mean is, say, 68 kilograms, no, let me use a round figure so it's easy to calculate. Let's say the mean weight of everybody who attends this class is 70 kilograms, right? So that's the mean, and a standard deviation of 5 kilograms, right? So the mean plus one standard deviation is 75 kilograms, while the mean minus one standard deviation is 65 kilograms, right? So if I say what proportion of values in the data set lie between 65 kilograms and 75 kilograms, the answer will be 68 kilograms. I'm sorry, 68%. I don't know if that's clear. We have a mean of 70 kilograms. So that's the mean. We have a standard deviation of 5 kilograms, right? And so 5 kilograms. So the mean plus one standard deviation is 75. The mean minus one standard deviation is 65. So if I now ask a question, what proportion of values in the data set lie between 65 and 75 kilograms? You will tell me 68%. So I don't know if it's making sense now. So if I now say what proportion of values lie between 70 kilograms, that's the mean, and 75 kilograms, what will be the answer? Type it in the chat box. No chorus answers because it's quite a large class. What proportion of values will lie between 70 kilograms and 75 kilograms? Type in the chat box. What proportion? So proportion, I want to see percentage. What proportion of values in the data sets will lie between 70 kilograms and 75 kilograms? So it's 34%. So we are getting it, So now, if I now say, so with this, I can set 10 MCQs from just with this mean of 70 and mean of and the implementation of kilogram. So what proportion of values will lie above 70 kilograms? What proportion of values in the data set will lie above 70 kilograms? Type the answers in the chat box. What proportion of values lie above 70 kilograms? Remember, 70 kilograms Yes, people are getting it now. So if you keep it just like that, we can just play around this. So we can play around this a while, but this is just keeping it simple, right? So what proportion of values lie between 60 kilogram and 80 kilogram? What proportion of values lie between 60 kilogram and 80 kilogram? Type your answers in the chat box. What proportion of values lie between 60 kilogram and 80 kilogram with a mean of 70 kilogram and a standard deviation of 5? Okay, so 95%. So if you understand the empirical rule, you will not even get confused with all these this kind of thing, that kind of stuff. So if we have 95 kilogram, that means what we have left is 5%. So symmetrical, 2.5 on this side, that is here 2.5, here 2.5, because the area, that's what is not on this slide. The area under the normal curve is 1 or 100%. The area under the curve is 1 or 100%. So type in the chat box, what proportion of values lie below 60%? What proportion of values in the data set lie below 60 kg? Sorry, not percent. What proportion of values in the data set lie below 60 kilogram? What proportion, please type in the chat box, what proportion of values lie below 60 kilogram? Yes, 2.5%. So people are getting, so understand the proportions under the curve, at least from the empirical rule. Let's start with that first, before we now move on to, and all that. So what proportion of values in the data set, type in the chat box, what proportion of values in the data set lie above 60 kilogram? So with this, I can set 15 MCQ. What proportion of values in the data set lie above 60 kilogram? Remember, we have a mean of 70 and a standard deviation of 5. We have a mean of 70 kilogram and a standard deviation of 5 kilogram. So what proportion of values in the data set? So you have a data set, so many weights, you have measured so many things. But we have told you that, okay, let's say the sample size is large. They've told us that it's normally distributed with a mean of 70 kilogram and a standard deviation of 5 kilogram. What proportion of values in the data set lie above 60 kilogram? Type in the chat box. I want more responses, so let me know whether you are understanding or not. Again, so let me pick. So for those who have responded, I will call somebody out now to tell me how you got your answer. There's nothing to calculate, right? Someone is saying that, well, how did you calculate? There's nothing to calculate. If you understand this diagram that is before you, you understand, then we can always play around with the figures. So if we say the middle here is 70 kg, just looking at this green diagram before you, all these questions, you can answer them if you understand the characteristics that we're talking about, right? So if I say that the mean is 70 kilogram, if I say that the mean is 70 kilogram, right, and the standard deviation of 5, so this is 70 kilogram, right? A standard deviation of 5 means mean plus 1 standard deviation, that's 75. Minus 1 standard deviation, that's 65. Minus 2 standard deviation, that's 60. Minus 2 plus 2 standard deviation, That is 80. So already that gives you this. So that is those figures I'm just playing around with. So definitely, if I say what proportion of values in the data set, because the area under the curve is 1 or 100%. So if I say what proportion of values in the data set lie above 60, we know that 60 is the mean minus 2 standard deviations away from the mean. So here is 60. So what proportion lies above? That is all the proportions to the right of this. So already we know that this is 97.5%. Because anything below this is 2.5. So even though I can play around this, I can say what proportion lies above 80 kg, what proportion of person lies below 80, what proportion lies above 65, what proportion lies below 70, I can just play around with the figures based on just this standard, based on this normal distribution curve that is before. Okay? So for those who it's a large class, so I don't know. I thought this slides was already given to you, so you go and study, at least read around and all that. You get, but obviously you just received it and dumped it. Okay, so importance of the normal distribution, very, very important in inferential statistics. If you don't understand this, you don't understand the things we're doing in inferential, at least the principles behind it. You get, so it's important. This very, very important in inferential statistics. So all that we are talking about is the normal distribution. So we have what is called the standard normal distribution. We can transform individual values from the normal distribution to a standard normal distribution. So I don't know where you saw 2.4%, though. I never said anything about 2.4. I don't know who is writing 2.4 there. We didn't say 2.4. We said what? 2.5, not 4. Because if you add those numbers, they're supposed to give you 100% on 50 on one side, 50 on the other side. The entire curve, 100%. So please type well so that we know what we are passing to the group. So that is normal distribution. We have the standard normal distribution. So we have the standard normal distribution. So for the standard normal distribution, we are converting individual scores to a standard score. So in this case, the mean is 0 and the standard with a standard deviation of 1, right? And how do we transform an individual score to a standard score, right? It's just a simple formula. The individual value minus the mean divided by the standard deviation. So all those figures I was using and all that, that is the normal distribution. But we can standardize this normal distribution to a standard normal distribution, whereby we have transformed these individual values in the data set to standard scores, right? And so this is the diagram that best fits it. So all those things we're saying plus or minus 2, those are, all these are individual values, but we're standardizing it to a standard score. So what is the value that we have? So this standard score is known as the z-score. So that is known as the z-score. So what is this z-score? We have transformed an individual value x to a standard score. And the formula for that is the individual value minus the mean divided by the standard deviation. The individual value minus the mean divided by the standard deviation. So that's how we convert a normal distribution to a standard normal distribution. And that is where we got the Z table. Remember, in secondary school, for those of us who have children in secondary school, or if you can remember your secondary school days, there's the 4-figure table. We have the Z table. There's one of them that is the Z table. This one of them is the Z table. So We are transforming individual values in the data set to a z-score for us to be able to use this z-table. What is the function of this z-table? We can get proportions under the curve. Now we have used the simple +1 -1. So using that same example here, what if I tell you that what proportion of values in the data set lie above 62 kg? We may not be able to know because 62 doesn't fall on this our +1 +2. So that is where this z-table comes in for us to be able to answer that question. So the z-table gives us the proportions under the curve, and then we can relate it. So let's see, now look at this table. So there are different variations of the z-table or versions of the z-table. Looking at this gives you proportions from the mean. You can see the shaded area. So this gives you proportion from the mean to the value of z. Compared to this, just look at the shaded area. You can see it's from the middle. And if you read it, it tells you, it gives you starting from the middle, z equal to 0. Remember, in a standard normal table, the mean is 0 and the standard deviation is 1, right? So this z-table, this version of the z-table, gives you a proportion from z equal to 0, that's the mean, to the value of z, right? So the proportion that you're looking for, of course, you will work it out from the mean, that is from the middle. Compared to this version that gives you the proportion, or the proportion to the left of that z value. So you can see the shaded area here compared to the shaded area here. So if you know how to use the two tables, it will still give you the same answer. So let's calculate. Let's use, we used a mean of 70 and a standard deviation of 5, right? So let's convert, somebody should just type in the chat box, type a score, and an individual weight. Remember, we're using weight as our variable. So 70 kg mean, standard deviation of 5. So someone should just type a weight, a value of a weight there. Let's see if we can transform it. Okay, let's use 85. I think that's the first one I'm seeing. 85. So we'll convert 85 to a z-score. So let's do that. So 85 minus our mean is 70. So 85, calculate to 85 minus 70 divided by what? What's our standard deviation? 5. So that gives us a what? That gives us a z-score of 3. This is really high. So that gives us a z-score of 3. This table was cropped, so it didn't reach 3. So let's use another. This table continues, so it's just, it was cropped, so it's cut, right? But let's use a value that is within this table. So I'll show you how to get the proportion under the curve. So somebody did 78. 78 may still be too high. So put another weight on the group. Okay, no, 65 will still give us our value. I want us to use a value that 60, 65. We know that 60, if we calculate 60, it gives us -2. I already know the answer. I want something that is in between so that we use the table. Because if it's 60, I may not need the table because 60 is already -2, and that gives me the answer. Okay, so let's use 55. No, 55 is 55. 55 see the same thing. That 55 is -3. 67. Let's use 67. I want us to use something that is in between. So let's use 67. So let's work out the z-score 67. So 67 minus 70. 67 is our individual weight minus our mean, which is 70. And here, this one gives us -7. So that's good. Divided by, what's our standard deviation? 5. So that gives us minus what? What did you get? Minus 0.6. Yes. So that's the same thing I got. minus, so somebody did not put the minus there, minus 0.6, so that you know that this value is less than the mean. I don't know if you understand. For us to have a minus, it means that that individual value is less than the mean. So we have gotten minus 0.6. So we have transformed the individual value of 67. Is it 67 we said? Yes, 67 to a z-score of minus 0.6. So we will come to this table. We can see z is 0. So remember.
Please, I have question.
Wait first, let's calculate finish. So that the people that understand will understand this part, then we can now come to people that are not understanding anything at all. So this z table now is giving us the proportion between 0 and 1.1 and the value of z, right? So let's assume that we're looking for the proportion between, so if the question is what proportion of values in the data set lie between 67 kilogram and 70 kilogram. So that let's assume that's the question. What proportion of values in the data set lie between 67 kilogram and 70 kilogram? We know that 70 is our mean, right? So if we're using this table, remember that it is symmetrical about the properties of the normal distribution is that it's symmetrical about the mean. So the proportion we will get from 0 to z equal to 0.6 is the same proportion we're going to get from z equal to 0, which is the mean, to z equal to minus 0.6. Remember, it's symmetrical about the mean. So 1/2 is the mirror image of the other. So whatever proportion is from z equal to 0 to the positive value of z is the same proportion from z equal to 0 to the negative value of z. So we have gotten 0.6 minus 0.6. And the question says, what's the proportion between 67 to 70 kilogram, which is our mean? So we're looking for the proportion between from z equal to 0 to z equal to minus 0.6. Also remember, z equal to 0 to z equal to minus 0.6 is the same proportion from z equal to 0 to z equal to plus 0.6. So we'll just come here, z 0.6. So of course we don't have other decimals or fractions. So we'll just do z equal to 0.6, which is 0.2257. So the proportion from z equal to 0, which is the mean, to z equal to minus 0.6 is 0.2257. That is 22.57%. So that's how to interpret this thing. This particular one. So I don't know if I've gotten the proportion. But if we say we are using what proportion is between 0 and z equal to 0, what value did we say? So let's say 75 kg. 75 kg gives us a z value of 1 plus 1. So you can see plus 1 is what? 0.3413. That is 34%. So that's how we got our 34. That's how we got our 34. Z equal to 1 is 34%. Remember our proportion. So if we say 75 kg, what proportion of values lie between 70 and 75 kg? We already know that 75 kg is plus 1 standard deviation away. But if we're transforming into a z-score, which you should to be able to use this z table, you will transform it 75 minus 70 divided by standard deviation, which is 5. So 75 minus 70 is 5 divided by standard deviation, which is 5. 5 over 5 is 1, a z-score of 1. So between z equal to 0 and z equal to 1 is 34%. It will still be the same thing as what we did. Right. So it's a lot to take in. This table, you see the same thing as this one. So you can see the full, you can see it's full now. So you can see z equal to 3, 0.4987. That's 3.0, 0.4987. And don't forget this particular Z table gives you proportions from the mean. So you see you can see Z equal to 3.49 is 0.4998, almost 0.5. Right? Compared to this curve that gives you can see from -3 counts down because it gives you cumulative probabilities. So whatever it is you are calculating, it gives you whatever you calculate as a Z-score. You can let me show you the shaded aspects of it. So you can see if it's -3, this particular curve takes into consideration the area under the curve, that is the entire curve, unlike this one that takes into consideration just half of the curve. Then you interpret accordingly. If you use the two tables, you get the same results. So that is basically that. I know it's a lot to take in, but if you go back and digest it, work with online resources and online materials, it's really pretty simple. Really pretty simple. Okay, so I think I will just end here. It's a lot already. So let's go back and digest what we have really learned. But what I would say is that the types of distribution we have, right? You can have discrete probability distributions and continuous probability distributions. I can say the types there. So the normal distribution follows the continuous probability distribution. That's what you see here, right? So just note the types of distribution under discrete or continuous, right? So that is about that. So you have other distributions and all that. So the T distribution mirrors the Z distribution or the normal distribution when the sample size is large. When the sample size is large. So that's why when you are doing independent t-test and all that, if the sample size is large, the formula for the t-test and the formula for z-test is literally the same. Because as the sample size increases, the t distribution will mirror the z distribution as the sample size increases. So, but let's go back and digest these things. But again, like I said, there are statistical tests, there are all that gives us the z-score, z-value, all those things. But I'm just trying to make you understand how this is done. So nobody expects you to be knowing that maybe I'll bring out table and all that. No, really. But maybe just if at all I want to ask this kind of questions, I'll just play around this +1, +2, because it's, basically those simple things. But I just took my time to explain how the Z table is used so that you can really understand. Because you just ask yourself, what are all these figures just up and down the place? So that is that. But rarely would we tell you, because it may not be people come and sit down in the exam hall and be writing. Most of your tests and all that will be online and all that. So nobody will give you tables and all that, right? But just to make you understand, if at all I want to ask you questions around the normal curve, I'll figure out a way to do it that it's easy to, maybe it's +1 or -1, +2, -2, and then it will follow the empirical rule, really. Yeah, to just make it easy enough. But I just went overboard to really explain how most of these things is done. Okay, so that's that. Any questions? I think we can end it here today because it's a lot. Don't tell me you don't understand, because I don't even know where to start from if you say you don't understand. But there are certain key things that you want me to just throw more light on. I think you can. You have the slides already, so just go back and build on it. Because it's not one lecture that will make you understand all this. So you go back and build on it, read wide, watch online videos, YouTube and all that. They're simple enough and you can understand it. Okay, any questions? So what we call the empirical rule is just, well, that's just the name, but really it's just to tell us the 68, 95, 99.7 rule. 68% of the values in the data set lie within one standard deviation away from the mean. That is above and below the mean. 95% lies within 2 standard deviations and all, and away from the mean. And 99.7 lies within 3 standard deviations away from the mean. So that is just what we mean. And we have done some examples to show you how you can work out these proportions under the code. It's sounding abstract to you. Unfortunately, I don't know how to help you if it's so abstract. Go and read the slides. The slides alone may not do justice. So you need to go and read other resources, online materials. There's so many normal distribution. Just Google normal distribution. So many materials will come out. And you can, in this day and age, there are a lot of resources online, from textbooks to videos to everything. So just get the basics from the slide and just build on it. Okay, any other thing? It's 2.5% to anything above or below 2 standard deviations away from the mean. 2.5 on each side. So like, if you remember, I said the area under the curve is 101 or 100%. So if I've gotten 95, what is left is 5, right? So anything above that is 2.5, symmetrical about the mean. So 2.5 on the left, 2.5 on the right. Yeah, so that's about that. Okay, so no other. Read about the normal distribution, read around it, look around how questions on the normal distributions come, and all that. It will just make you, it's not as hard as you think it is, honestly. Honestly, it's not as hard. If you guys remember the 68, 95, 99.7 rule, you know the fact that it's symmetrical around the mean. One half is a mirror image of the other. That puts a lot of things into context, and then you can attempt to do. So when we say 68%, you can see where the arrow is saying 68%. So if it's symmetrical, that means one side is 34, one side is 34. That gives you the 68. So you can see where the 95 is. All these sides is 95. We already have 68. What is left? 27, right? So we know that here is 34, here is 34. That gives you 68. So here and here is what is left. That's 27, I think. Yes. So that means this side will be 13.5. This side will be 13.5. So 2 standard deviations away from the mean is 95%. Because if you add 13.5 plus 34 plus 34 plus 13.5, gives you 95%. And then with the mean, with the standard deviation, we know what these values will be. And then we can do whatever proportions we need that fits into where those values will be, down to 3 standard deviations away from the mean. So it's the same thing. Okay, I know it's a lot, but please do well to go back, look at it, study, and it's not, what I can tell you is not as difficult as you are thinking it is. It's not. It's not. Honestly, if you go back and you study it very, very well, you say, is this what it is? It's very, very simple. Very simple. Okay, so in the absence of any other comment or question, and with a clear instruction that you should go back and study, so I think we can call it a day or a night. So sorry for starting the class late. I was still in transit. So thank you all and have a wonderful night.
Thank you, sir.
Thank you, sir. Thank you, sir. Bye.
Thank you.
Thank
Doc.
you, sir. Good night.
Thank you, sir. God bless you.